Welcome back to lecture 10.1, where we're going to talk about the kinetic theory of gases. Okay, so the first thing is that last time we explored the scenarios of changing the density, changing the pressure, and changing the temperature with altitude, and we came up with the concept of the adiabatic lapse rate. So this time we're going to talk about the kinetic theory of gases, but beforehand I want to in class do an example, and it's the example where we'll do an example where what we do is we have a box and we have two gases with a partition in between, and that partition can actually switch from being just a physical membrane to one that's also insulating. And so we're going to set up the situation, remove the insulation, and then see how the system equilibrates. Okay? So that's the example we're going to do in class, and then we're going to come along now to lecture 10.1 and ask ourselves, now that we've gotten pretty good at thermodynamics, now that we've dug in pretty far, can we answer some slightly deeper questions? Can we, for example, answer why, for an ideal gas, does PV equals nRT and U equals NCVT? Okay, so we're asking, these kind of questions we've gotten. Can we understand these really from a microscopic point of view, right? Can we understand where these originate from? Okay, so we're going to invoke this kinetic theory of gases, and we're going to describe it, and that's really going to tell us that. Now, we are going to look at this thing in terms of molecules, right? Atoms and molecules. But we aren't going to think about this from a quantum mechanics perspective. It's still going to be very much a classical perspective, okay? So we're not going to have the things that we needed in StatMac, for example. We're simply going to think about these things from the kinetic energy, okay? So the thing is that a gas is made up, so there's a few guiding principles here. It's that a gas is made of atoms or molecules, atoms/molecules, that behave randomly. What I mean is that we're going to think about, for example, the force that molecules apply on a wall. And it's going to be clear that all the molecules in the room don't gang up and push on that wall, right? They push on all the walls, and they push on the wall randomly. Also, another guiding principle is that the collisions between molecules are going to be elastic, right? That is that they conserve energy. They're going to just transfer momentum between them, but they're not going to change the energy. So we're not going to have inelastic collisions that, for example, excite electronic energy levels in molecules or change the nuclear structure in any way. And we're also going to neglect interatomic or intermolecular forces. We're not going to worry about any potentials that change when we get close to each other. That is everything, right? Our entire internal energy, U, is only dictated by our kinetic energy. All right. So reminding ourselves, what is the kinetic energy of a gas? Classically, it's simply 1/2 mv squared. Right? So that's all we're going to need to understand. Okay? This is in particular true for a monatomic molecule where we just have its center of mass. We're only going to have a kinetic energy. For a diatomic, we could also have the rotational energies, but we'll see how those come into play later. Okay, so just like we always do in physics, we want to understand how a gas is treated in 3 dimensions. We're going to start with a simplified model. Let's start with 1 dimension. Okay? So let's start with the simplest thing we can do. Let's have a single atom of mass m having a velocity v. Okay? And we're going to put it in a 1-dimensional box having length L. We're only going to allow it to travel in 1 dimension. Okay? It's only going to be allowed to bounce back and forth. Okay, so what we're going to want to do is we're going to want to calculate the force that this applies to this wall. And so the average force is simply going to be from the impulse, right? The changing momentum per unit time. So we can ask, what's the per unit time in this system? So this is, for example, the force, the average force on the right-hand side. Let's just consider one side for now. So this just means the average, right? The bracket notation just means the right-hand side. I mean the average. Okay, so we're going to have a changing momentum per unit time. This is the impulse. This is a force. So the time it takes is simply the time it takes to traverse from one wall around and back again. Okay? So this is simply going to be the distance divided by the velocity it is. Okay? And the momentum change, right? So what's the momentum of a molecule? It's simply mv, right? But if a molecule bounces off this wall, for example, it has mv going this way and then mv going this way. So the change in momentum is 2mv. And I really should make sure that that's a lowercase v. Okay, so the average force applied is going to be 2mv over 2L over v, which is mv squared over L. Perfect. So this was in 1D. And now let's imagine in 3D how we deal with this. So let's imagine a 3-dimensional box. And we're going to make every single side length L. Okay? And really this is a unit box in X, Y, Z plane. All right, couple of notes. First, that the volume is going to go like L cubed, of course. And we're eventually going to put N atoms in it. But let's start by putting a single atom or molecule in it with mass m and give it a velocity v. Okay, so now again let's consider the force that we apply on the right-hand side wall, right? So here we had the force in the x direction was mv in the x direction squared over L. Let me be a little bit more clear. I actually want n atoms, but first, atom I. We're going to have an atom labeled with an indice I. So we're going to say that the force from atom I on the x wall x is mvix squared over L. Just exactly what we had here, but now we're specifying that it's for a particular atom and that we're going to have a lot of them. All right, so that the average force, we actually now want to add up all of the atoms. So we're going to run that from 1 to n of Fix. So that's the sum from I n of m Vix squared over L. But there's a problem. There's a problem with this concept. So this was perfectly fine in one dimension. Now we've figured out how to label that it's one of the dimensions in a three-dimensional space, and we've figured out how to account for all the atoms. We're going to do this summation. But what we haven't realized is, hey, I said all the atoms don't gang up and only go one direction. They have to move randomly, right? So if this atom has to move randomly, how do I know, if it's moving in some arbitrary direction, what the momentum is, okay? So now I'm going to have to need a mean squared speed. Okay? So, what do I mean? This was a velocity, but I really want to, for kinetic energy, all I care about is its speed. So all I really care about is the average of it, right? So I can imagine having this, the average speed of all the molecules is the sum from 1 to n of all the individual molecules, right? Divided by the number of molecules. So this will be the average speed. But this is in some arbitrary direction. So I'm going to have to say that this is really some possible combination of the motion of it in the x direction and the y direction and the z direction. Right? It could be moving in any direction, and since it's the average squared, the velocity squared that we care about, we're going to have a mean squared speed. So I can rewrite this simply as the average of Vx squared. So V squared is Vx squared plus Vy squared plus Vz squared, where Vx squared is this sum. Now, there's a key feature, is that since this is at random, right, all three of these dimensions must be the same. Okay? So any of my dimensions, right, must be the same. Whoops. So really, they're all identical, so I could just add up all three of them. Sorry, 3 times. Or Vx squared is 1/3 the of the v. Okay? So on average, the speed in the x direction is a third of the average mean squared speed. All right? The average of the speed squared in the x direction, the velocity squared in the x direction, is a third of the mean squared speed. Okay. So now we can put that into our force, right? So our force, we are going to do this summation, right? And so now we have m. We do the summation over all of them. There's n of them. And then you get this average that we had over here, Vx squared over L. So our average force is now m. So it's 1/3 m n over L v squared. Perfect. Now, in 3 dimensions, when we think about, say, this thermodynamic variables that we're looking for, we're not looking for the force. We're, of course, looking for the pressure. The pressure is just that average force per unit area, which is that average force, but the area of the box side is L squared. So we're simply going to have 1/3, let's just write it as, yeah, that's fine, 1/3 m n over L cubed v squared, which is 1/3 m n over v squared. This v is our volume, right? I just replaced L cubed with the volume. Okay, so if we rewrite that to be a little bit more transparent, we're simply going to move my v to the other side. I have PV equals 1/3 m n v squared. Perfect. So let's take a pause. And look at our internal energy. So different calculation. Let's look at our internal energy. Well, we said it only has to do with the kinetic energy. All right? So what's the kinetic energy of a single atom? So a single atom would be 1/2 m vi squared, right? And I'm simply going to sum over all of them. That sum is just going to bring out an n v squared. It's their average velocity. Okay, so now let's inspect. We have PV equals 1/3 m n v squared. U is 1/2 m n v squared. Well, the number of atoms we could rewrite as n, the number of moles, times Avogadro's number. So we could have PV equals 1/3 m n na V squared. And U is 1/2 M N A V squared. Let's remember what we wanted. We were shooting for PV equals nRT, and U was nCV_T. So that's why I rewrote it like this, so I could get my n dependence. So now we have to ask, okay, this would be totally consistent if RT was equal to M NA B squared times 1/3. Because for a diatomic, forgive me to make that more clear, this is because for a monatomic gas, that was equal to 3/2 nRT, remember. Okay, so let me rewrite that as 1/3 M B squared equals RT over M and A. I'm going to put the 3 over there, but then I'm actually going to multiply each side by 1/2. Okay, so these would be consistent if this were true. So now does this make sense? Well, when we were talking about heat capacities, if you look back in that lecture, about heat capacities, we found the correlation between the R is simply R over NA is equal to KB. Oh, I've made a little mistake. Got my M twice. So KB is called Boltzmann's constant and is 8.314 joules per mole K divided by 6.02 times 10 to the 23rd atoms per mole. So if you calculate that out, it's 1.38 times 10 to the minus 23 joules per Kelvin. So this is Boltzmann's constant. It is R over NA. So what we've said there was 1/2 M V squared is equal to 3/2 KB T. Does that look familiar? It should be, because this is saying that the average kinetic energy per atom is simply 3 times 1/2 kBT. This is the equipartition theorem. Rearing its head again. I think that's beautiful. So if we just start with the idea of the momentum transfer and kinetic energy of a single atom and invoke our equipartition theorem, we can derive the ideal gas law and the internal energy of an atom, internal energy of an ideal gas from first principles. Right? These are really standalone first principle ideas. Okay, so now let's briefly take that and extend it to the idea of 3 dimensions. So now let's just take a quick break and we'll do a short one where we do the kinetic theory of a diatomic, not 3 dimensions, of a diatomic molecule.